We now need to learn about a new type of number called a complex number. Now in the past you've learned all about the real number system. You learned what its structure was. You know you had your natural numbers, you've got integers, you've got whole numbers, rational numbers, irrational numbers, etc. Now the basic structure of the real number system contained all those numbers I just mentioned. We're about to learn about something called the complex numbers, which we're going to start off with when we get ready to talk about the complex numbers. We're going to talk about a group of numbers called imaginary. Alright, now your imaginary numbers come as a result of a need to be able to take the square root of a negative number. For example, if you had an equation that you needed to solve, like x squared equals -1, we know that we can't solve this equation in the real numbers because you can't square anything in the real numbers and get a negative answer. So when we attempt to take the square root of both sides to get x, we get x equaling the square root of -1, again, a non-real number, and we have problems with that. So we introduce something called the imaginary numbers. The very first imaginary number we need to mention is I. Yes, we do use the symbol I to represent what's known as the imaginary unit. And it just so happens I is this square root of -1 that we couldn't figure out over here in the real numbers. So your imaginary numbers, your purely imaginary numbers, are numbers like I, 5i, 3i, -3/4 I, etc. So that's our first group of numbers outside the real. Now we need to also look at a larger group of numbers, which is actually our main theme here, called the complex numbers. Complex numbers are a result of a real number being paired with an imaginary number in this type of form. Say -3 plus 7i, 4 minus 5i, 1/2 plus 3/8 I. So therefore, technically, all of your real numbers are also complex numbers, because if you pick any real number like an 11, it can be written as 11 plus 0i. All of your imaginary numbers are complex as well, because you could write it as 0 plus 4i. A lot of times I'll refer to your purely real numbers or your purely imaginary numbers as meaning having this 0 component. But again, in reality, the real and the imaginary are a part of the complex numbers. And again, the complex numbers are a result of taking the square root of a negative number. Now, I comes from taking the square root of -1. What if I had a square root of a -16? Well, I could say that the square root of the 16 is 4, as we already know, and the square root of the negative just brings out the I. Square root of -100. Square root of the 100 would be a 10. The square root of the negative is the I. Now, as a result of this, when you start raising I to higher powers, an interesting pattern develops. I, of course, to the first power is just I itself. I square is the square root of -1 times the square root of -1, which is -1. I cubed is the square root of -1 times the square root of -1 times the square root of -1 once more. These two give you a -1, or a negative. This one gives you the I back. I to the 4th then. Again, another interesting pattern. Square root of -1 once, twice, 3 times, 4 times. So this one will be a -1. These will be a -1. -1 times -1 would give you a +1. That pattern allows us to take I and raise it to any power we want, and we know that one of these 4 values will be the result. Like I to the 21st pattern. If we take 21 and divide it by 4. Divide it by 4 because this fourth power just gives us a 1. We would have 5 times 4 being 20 with a remainder of 1. So that means that I to the 21st is the same as I to the 1st, which is I. So in I to the 105th power, we will take that 105, divide it by 4. Whoops, doesn't go 5 times. Not bad. Goes 6 times. 6 times 4 is 24. Again, a remainder of 1 means that's an I again. So the remainder alone tells you remainder of 1, it's I. Remainder of 2, it's negative 1. Remainder of 3, it's negative I. And no remainder at all, it's a 1. So I is pretty easy to raise to a power. As a matter of fact, while we're at it, you might as well see how this can be done on your calculator. Now, if you're going to be working with the imaginary or the complex numbers, you might want to go in to hit your mode button and move down the page here and move it away from real to the A plus BI mode. And once you put it in that mode, you can pretty much leave it there. It really won't give you any trouble from here on out. But notice that your I is above your decimal point. So you'll hit second function, decimal, bring up your I. If I want to raise it to the 11th power, then it will tell me that's 1 times 10 to the negative 13 minus I power. It probably means it's going to be a, well, actually the calculator's having a trouble with a higher power, which I hadn't realized it might do. We can do that one, actually 11th power on our own. Take the 11, divide it by 4. 4 goes twice. Remainder of 3, third power, that's a negative I. So I to the 11th power is negative I. We were actually able to do it by hand much better than the calculator, didn't it? Did it? I believe it. Didn't think it would have problems with it that quickly. Let's see what else we can do with I. Now this next stuff we're going to do, the calculator actually can do that. Powers sometimes give it trouble, sometimes quicker than I thought they were going to. But for your addition, if we had a 3 plus 2i and we were adding a 4 plus 7i, when you're adding these complex numbers, all you have to do is add the real to the real and the imaginary to the imaginary. So we would simply say 3 and 4 is a 7, 2 and 7 is a 9, and we put the I on. So try that again. Let's take a 4 minus 6i and add to that a 5 plus an 11i. We would say 4 and 5 gives us 9. Negative 6 and positive 11 is a 5i. Now when you subtract, like a 3 minus 7i minus a 5 plus a 4i, you have to remember to distribute your minus sign. So 3 minus 5 would be a negative 2. Negative 7 minus a 4 would be a minus 11i. Like I said, your calculator can do these quite easily. If I wanted to put in a complex number, I'd start with the left parenthesis, and I could put in 4 plus, second function decimal would be 4 plus I, plus, open another parenthesis, 8 minus 4, second function, I, close the parenthesis, and you get 12 minus 3i. Works easily for addition, works easily for subtraction. So remember your i's right here, typed in the way you see it, and the calculator will do a perfectly good job of addition, do a perfectly good job of subtraction. Now let's look at how the multiplication works. Clear off the old problem. Alright, now the multiplication. If we had a problem like 4 minus 2i times 3 plus 5i, This should remind you of two binomials being multiplied. That's not what it is, but it should remind you of that. Remember, your technique for multiplying binomials is foiling. And we can do something that looks just like foiling to work this type of problem. First times first would be a 4 times 3, which is a 12. Your outer product would be a 5 times a 4, which would be plus a 20i. Your inner product would be a minus 6i. And your last times last will be a minus 10. Watch your power really carefully, 10i squared. So we will combine 12 plus 20 minus 6 is a 14i. And remember that I squared means negative 1. So this minus 10 times I squared becomes a minus 10 times negative 1. So this becomes 12 plus 14i plus 10. When I combine terms one more time, I get 22 plus 14i. So let's see if we can duplicate that on the calculator. Left parenthesis, 4 minus 2, second function, decimal is your I. Bring up your right parenthesis, open your left parenthesis. Again, remembering the other number was a 3 plus 5i. We'll start typing it in. 3 plus 5, second function, decimal brings up the I, closing the parentheses. We get a 22 plus 14i, which was exactly what we said it was. So the multiplication looks just like foiling. Remember, you have to combine the i's, and the I squared becomes a negative 1. So let's try one more by hand. We will then check it on the calculator, and then I'm going to show you what type of equation can give you these types of answers. Let's take a 3 minus 7i, multiply it by a 2 plus a 10i. Again, first times first is a 6. Outer product is a plus 30i. Inner product is minus a 14i. Last times last would be minus a 70i squared. So the 30 minus the 14 would be a 16i. The minus 70 would become a plus 70 because the I squared would become a negative 1. So when we put it together, we're going to have 76 plus 16i. And again, on your calculator, left parenthesis, 3 minus 7, second function, bring up the I, close parentheses, open the other one, and 2 plus 10i was the other number. So I have 2 plus the 10, second function, bring up the I, close the parentheses, hit enter. 76 plus 16i was exactly what we got. So that's how you multiply and add and subtract these complex numbers. Now, there's another issue with the complex numbers we need to be aware of, and that's something called a complex conjugate. It's a pretty simple idea within itself. If you have a complex number in the form a plus bi, its conjugate is going to be a minus bi, and therefore the conjugate of a minus bi is a plus bi. Now, when we multiply complex conjugates, let's look at an example on the calculator. Let's take a 2 minus 8, second function, bring up the I. So 2 minus 8i would have for its conjugate a 2 plus 8i. So those would be conjugates of each other. Now, when you multiply a complex number by its conjugate, what we discover is we always get just a simple real number, no imaginary component. That's very convenient if you are asked to divide. If I had a 5 divided by 2 minus I, to do this division, you don't actually do a true division. You do multiplication, both top and bottom, by the conjugate. So here, multiplying, we get 5 times 2 is 10, plus a 5i. On the bottom, we get 2 times 2 is 4. And as you do your inner and your outer product, you're going to get a plus 2i and a minus 2i. Last times last is going to be a minus I squared. The reason this turns out the way it does is because the 2i and the negative 2i cancel. 4 minus I squared becomes 4 plus 1. So we've got a 10 plus a 5i over a 5. And we can divide the 5 out and get a very simple complex number for that result. So, again, if I had a 6 over a 3 plus 2i, I would multiply top and bottom by 3 minus 2i. And I'm going to leave that multiplication alone just for a second so I can get this down here. 3 times 3 is 9. I already discovered that the inner and the outer product cancel, so I'm not even going to bother doing them. I'm going to have a minus 4 squared. Alright, on top, you've got what we had before. 9 minus 4i squared becomes a 9 plus 4. So going ahead and multiplying. I get my answer. Of course, this type of thing, again, can be done on the calculator. If I wanted to take 7 and divide it by 5 minus 2i, type it in just like that. The parentheses are absolutely necessary. Now, when you hit your division and you do hit the enter, it gives you an ugly decimal. Of course, we can go back, math, option number 1, and ask it for a fractional answer. And that looks a whole lot better. So the calculator can add them and subtract them and multiply them and divide them for you without any trouble. Now, as promised, I want to look at an example of a quadratic equation that would have these types of answers. Now, if we go to our calculator and we look at x squared minus a 2x, and we do a zoom standard. Oh, wait a minute, that wasn't the equation I wanted, because what I want is one that doesn't hit the x-axis. And maybe, let's see if changing that will give me what I want. Nope, that just moved it. Let's try one more. Let's see. X squared minus 2x. I'm surprised that didn't work. Let me look at that one again. Again, I'm looking for something that doesn't hit the x-axis. Let's try. Oh, I think I know the problem. Should be not a x on there, but just a plus 2. And yes, we do have one that doesn't hit the x-axis finally. So, x squared plus 2x, it doesn't hit the x-axis. So if I was to say x squared plus 2x equals 0, I won't have, oops, and then I keep putting that x on there, x squared plus 2 equaling 0, I won't have two real solutions coming out of this. Now let's solve this using the quadratic formula. We've got a equaling 1, b equaling 0, and c equaling 2. Putting this in the formula, I get x equal to opposite of b, which would be a 0, plus and minus square root of b squared, which is 0, minus 4 times a, which is 1, times c, which is 2, all over 2a. So from this I get plus and minus square root of negative 8 all over 2. Now, whenever you use the quadratic formula and a negative shows up as your discriminant, meaning shows up underneath the square root, that means that you've got two complex solutions. And our two complex solutions would be, pulling out the negative, they come out as an I. Square root of 8 would be a 4 times 2. So it's plus or minus 2i square roots of 2 over 2. These 2's cancel. So from that we've got two complex number solutions. In this case they happen to be imaginary, but that's really not what mattered entirely, just that they were actual complex type solutions. Let's look at one more. Getting rid of the first equation, we'll put in 2x squared plus 4x plus 3. And again, what I'm hoping for is a graph that doesn't hit the x-axis, and that one doesn't. That means we will have two complex number solutions. Let's try this again with the quadratic. Alright, setting that one equal to 0, I'll have the 2x squared plus 4x plus 3 equaling 0. For this one, a equals 2, b equals 4, c equals 3. So x is equal to opposite of b plus and minus square root of b squared minus 4 times a times c all over 2a. So that is negative 4 plus and minus 16 minus 24 all over 4. Negative 4 plus and minus the square root of negative 8. Again, a negative number means two complex solutions. So it's negative 4 plus and minus 2i square roots of 2 all over 4. Notice that everything is divisible by 2, so this becomes negative 2 plus and minus I square roots of 2 over 2. So that's how you can use the quadratic